Welcome to episode 1 of the Digital Logic++ series. My name is Natan Ritholtz. At any time, you could click on the link description below and download the PowerPoint presentation in order to follow on easier with this program. This episode is about the overview and basic logic fundamentals. This course is designed for beginners for the hardware level of digital logic and circuitry diagrams. So let's begin. This series' objectives include to learn about Boolean logic and its implications for digital logic, to learn concepts behind logic gates and how to combine them to create circuits, to understand performance issues of circuitry and how to maximize gate resources in order to minimize these performance issues, and finally, to use and implement this knowledge that we have all learned in this course to create fully functional circuits to execute simple tasks, such as our very own calculator. A few important points in order to take in this course is that, first of all, it was tailored to get hands-on experience as soon as possible. So therefore, this course may miss significant historical information about key concepts within digital logic. As I have stated earlier, this is a beginner course. Therefore, there is no programming experience required. Now, that means absolutely nothing to do with any kind of programming language or any such topic. However, there are some key concepts that may be covered during this course that are relevant to the field of digital logic that require some background knowledge in computer science. However, that is not necessary in order to implement these circuits. Therefore, even though they may be a plus, it is not a requirement for this course. And lastly, make sure to have fun. Now let's start with the fundamental block of digital logic circuitry, Boolean logic. Now before I actually define what Boolean logic is, let's take an example here. We have a light switch. Now everyone knows that as human logic dictates, a light switch is usually attached to a light bulb. So therefore, in whatever position that the light switch is in, namely the off or on position, it would instantly dictate what position or actually what state the light bulb would be in, either the on or off position. So therefore, if the light is on the off position, it is said to be that the state result of the light bulb is off. And if it is on, then the light bulb would turn on. So just by visually seeing that light switch, let's call it A, is off, therefore we could say the result from the light switch being off is the light would be off. So now, Tim over here is wondering, all I see is the light switch. What am I going to say the result is? So because A is off, then the result would be off. But if A was on, then we could say that the light would be on. Boolean logic is almost exactly the same, except for the difference in on and off values are represented by binary digits. Therefore, on would be 1, and off value would be 0. But now that brings the question, is that all Boolean logic is about? Well, let's bring in a specific situation where Boolean logic would come straight into play. What if a light bulb actually had two different light switches that were attached to it? Now, I'm not going to say specifically whether if you need both on at the same time, or one on and one off, or what specific kind of combination is necessary, but just the mere fact that I've introduced another light switch has created a bunch of difficulties in terms of how is these two light switches, which we're going to name A and B, directly related to the result. Do we know instantly by looking at the light switches whether the light bulb is on or off? So that is what Boolean logic is devoted to. The first step to understanding Boolean logic is truth tables. Now, you may have seen previously in logic courses, in mathematical courses as well, truth tables like this. Now, if you've seen this, then you might be able to be eased a lot easier into truth tables. However, if you haven't seen it, it is not necessary. But if you have seen it previously, please understand that the truth and false values are replaced by the 1 and 0 values, respectively. Now we start with the different types of truth tables and what they represent. Now, if you've known in mathematical operators, a lot of the times we've used the dot operator or the plus sign in order to invoke multiplication or addition. However, it is important for you to instantly recognize there is a major difference within the truth table signs for Boolean logic. Therefore, A dot B doesn't mean A times B anymore. It means A and B. And A plus B means A or B. Now, to understand what this means, let us think about the light switches again. If light switch A and light switch B are both required in order for the light to be on, then we could say A and B, right? Because the key term here is A and B are necessary for it to be on. So now what the truth table does is it gives the different combinations for A and B within the different light switch positions, either 0 off or 1 on, and it gives the output determined on this condition. So because A and B is required for it to be on, if A and B are both off, then therefore the light is off. But if either B or A are on, just by themselves, it's also off. The only condition in which the light is on is when both A and B are on. Now let's look at A or B. The same situation is here. However, the difference is just by one of the two light switches being on, the light is on. And we could see that by saying either A or B are on. So we see B is on here, A is on here, and definitely in a case where both A and B are on, then the light would be on. Now let's look at two other gates. These are called NOT. NOT gates are just the inverse or the opposite of whatever the input is. In which case, if the light switch is off, then the light will be on. But if the switch is on, then the light will be off. This is the operator, the X bar operator, over whatever input is what makes it called a NOT. Now, for exclusive OR, that's what the XOR stands for. We have this plus sign with a circle around it. What it means is that if only one input is on. Now, there will be later conditions where we will see exclusive OR being a little bit different, but for our understanding now at this point during the course, we will just say that if there's two inputs within this logic statement, A and B light switches, that only when one of them is on, then the light is on. So we could see here, if both of them are off, then it is off. And if both of them are on, then it is also off. However, in these conditions here, where only one of them is on, then the light is on. And the last two gates here are the NAND, which stands for not AND, which is simply the negation of an AND statement. So that means the complete opposite. If we look back at the AND statement here, where the outputs would be 0, 0, 0, 1, here it is just 1, 1, 1, 0, which means in which case only AND would be correct here, where it's both A and B, then it completely negates the opposite of all of the output values for what is within this AND gate. And the same is for here, whereas either A or B would be 1 here, and definitely when both of them are here, it negates it and puts the opposite output. So now we have the 6 basic Boolean expressions and within truth tables for what we call as the 6 basic gates, which we will go into more detail about them in the next lecture. However, we are able to understand these 6 Boolean expressions within digital logic. There's a few important facts about these Boolean logics that one must understand before continuing. The negation of A or B is not the same as not A or not B. These are two complete different things. Within this one, we are taking A or B and nodding it, whereas here we are taking not A or not B. You'll see this later on when we start talking about the actual digital circuitry, that we'll see there are two completely different digital circuits. Now, one mathematical law that is brought up a lot of times within, outside even digital logic, within mathematical logic, is De Morgan's law. And we will be able to use that in order to minimize specific circuit problems. However, now it's best to learn it in order when we're learning about actual logic. That not A or B, meaning we are nodding the A or B statement, is the logical equivalent of not A and not B. And the same is not A and B, meaning we're nodding the A and B statement, is the equivalent of not A or not B. A few major properties that are necessary in order to learn about these logical statements are A and B is the same as B and A. And another statement is A or B is the same as B or A. Another rule is the distributive here, that A and B or C. And we will learn later on about parentheses, about specifically how they work. But whenever we see a statement where they are placed next to each other, without a dot operator, we can instantly put there an imaginary dot operator, so that these statements here, for example, are A and B and A and C. I will a lot of times swap in and out of using the dot operator. However, if you ever see a statement where two inputs are put next to each other without a dot operator, it could be assumed that they are an AND operator. So A and B or C is the same as A and B or A and C. This here is a double not, a double negation. So therefore, not A is the same thing as just saying A. A few identity rules here are A and not A is equal to 0. That's saying if the input is 1, and that means the negation would be 0, or even if this was 0 or 1, it will always be equal to 0 because it's an AND statement and we're talking about the negation. The same could be said about any input for A. For not A, it has to be 1 because one of them will be 1. A and 1 will always be whatever A is, and A and 0 will always be 0 since 0 is within the AND statement. A or 0 is equal to A or 1 is equal to 1. Now, for order of precedence, when we have different Boolean statements, there are different forms, like I've said earlier, that are put within inside it. And therefore, there will be different times that the same statement will mean two completely different things if read the wrong way. So in terms of order of precedence, it goes parentheses and not statements, then and statements, and then or exclusive or statements. So let's look at a few examples. Here we have a statement right here where if A equals to 0, B equals to 1, C equals to 0, what do you think the output would be? Now let's look. We have A, which is equal to 0, B, which is equal to 1, and C, which is equal to 0. However, due to the order of precedence, the AND statement will go first. So 1 and 0 is 0, and 0 or 0 is equivalent to 0. Let's look at another example. Here we have the same variables, however, they're put within a situation where there is parentheses around the statement now. What will the output be? Now let's look. we have 0 or 1, which is 1. And it's an AND to C, which is 0. So 1 and 0 is equal to 0. Now, you'll say to me, hey, look, it produced the same thing. However, if you look at these statements, they may look the same in terms of the result. However, they are a completely different logic diagram. As we'll see in later lectures, they actually look completely different and will produce different things dependent on the input. And lastly, let's look at this example here. Here we have a negation of an AND statement. So, let's see what it becomes. 0 is A. But here we have B and C. So first thing that happens is this AND statement, B and C, which is 1 and 0. So it becomes 0. And then we negate that 0, so it becomes 1. So that now this whole statement becomes 0 or 1, which is equivalent to 1. Next lecture, we will start talking about the actual digital logic diagrams for these specific examples which we were speaking of, and go through the 6 basic gates and how we could represent these Boolean logic expressions as actual diagrams.